What's going on, guys? Welcome to another video of Shadowx XM1's Garage. It has been a while, hasn't it? It has been, because I've been working myself hard. It gets a little more difficult when you start your bachelor's. Now, I can't complain too much because I've had it pretty easy. And looks like my next semester I might have it a little easy too. But, you never know. Now, there's one thing I will say that I am grateful for. It's time management. That's one of the things our heat transfer and fluid mechanics teacher pressed upon us time and time again. Time management. And that's one of the things several of my other instructors impressed upon me too. So without further ado, and without trying to make this longer than 5 minutes or more, and my apologies if it is, this is my first video project for heat transfer and fluid mechanics. So this is called the temperature scale. This will be due February 17th, 2023. So I figured I might as well go ahead and get it taken care of. Alright, guys. This is about how was the Fahrenheit temperature scale developed? 2, how was the Rankine temperature scale developed? Alright, now, my apologies if I get some of the pronunciations wrong, but this is me talking. This is me showing you what I found, what my research has come up with. Alright, now, without further ado, before I forget, let me shrink. Let me put myself over here. Alright, and I'll just, actually, I'll put myself down here. Might be a little better. Okay. Now, alright, now the first question is that we're going to answer, we're going to try to, said, why was the Fahrenheit temperature scale developed? Alright, I hope this answers the question thoroughly. This is on Today I Found Out, Feed Your Brain. www.todayifoundout.com. Now, I'll try to remember to keep these links open, and the links to the web pages that I found will be in the description box below if you want to look at them yourselves. Alright, why was the Fahrenheit temperature scale developed? Alright, let's see. Firmly entrenched in American society, the seemingly capricious nature of the Fahrenheit temperature scale could lead one to think that its Dutch creator, Daniel Fahrenheit, pulled the number for the freezing point, 32 degrees Fahrenheit, of water out of his hat. But in fact, its designation, as well as that of 0 degrees Fahrenheit, were precisely for the early 18th century calculated based upon deliberate choices about how to establish fixed points of temperature. Alright, engineer and physicist and glassblower. Hey, how about that? Mr. Fahrenheit, from 1686 to 1736, decided to create a temperature scale based upon 3 fixed temperature points: that of freezing water, human body temperature, and the coldest point that he could repeatedly cool a solution of water, ice, and a kind of salt, ammonium chloride. It is generally thought that he chose these 3 points based on an older temperature scale created by Ole Christensen Romer, 1644 to 1710, 20 years earlier. Alright, under Romer's system, brine, the salt ice water mixture, freezes at 0 degrees. Water at 7.5 degrees. Normal human body temperature was 22.5, and water's boiling point was 60. Desiring to make calculations easier, in other words, produce fewer fractions and to increase the precision of the scale by increasing the number of distinguishable parts within it granularity, Fahrenheit decided to multiply each factor by a factor of 4 and set to work. Now, according to his published article on the subject, he started with the brine and a blank thermometer. He then assigned the point where the thermometer was the lowest as 0 degrees Fahrenheit. Next, he placed the thermometer in still water just as ice was beginning to form. He eventually assigned this 32 degrees Fahrenheit. He then measured human body temperature and assigned this 96 degrees Fahrenheit, or sometimes it's 98.6, 97.9. It sometimes varies, but usually it's 96 degrees Fahrenheit. He ultimately chose these two numbers as opposed to 30 degrees Fahrenheit, or 7.5 if degrees or 4, and 90 degrees Fahrenheit, 22.5, 4, in no small part due to the fact that the 64 degrees between the 2 points made marking lines on the thermometer easier due to the 6 equal intervals. All right. Now, as water at sea level and standard atmospheric pressure boils at about 212 degrees Fahrenheit, in the original scale, 180 above its freezing point, this number was eventually defined as the scale's exact boiling point of water. This more precise definition ultimately forced a slight adjustment of normal body temperature to about 98 degrees Fahrenheit from 96 degrees Fahrenheit. What I tell you, of course, normal body temperature is a bit of a misnomer here. My apology if I butchered that, with it varying from person to person, and even varying quite a bit in an individual based on a variety of factors, such as time of day, age, etc., etc., commonly ranging between about 97 degrees Fahrenheit and 99 degrees Fahrenheit. All right, so there you go. All right. I think that was, basically. Okay, how now? Why was the Fahrenheit temperature scale developed? There you go. How was the Fahrenheit temperature scale developed? Well, that kind of answered both questions. Now, how did we end up with both Fahrenheit and Celsius scales? Well, I'm not going to read all of this, but I will read the highlighted part. The Fahrenheit scale was first proposed in 1724 by the German physicist Daniel Gabriel Fahrenheit. Using a tube filled with mercury or alcohol, Fahrenheit determined his scale based on 3 points. He set the point at which water, ice, and ammonium chloride, a salt, stabilized as 0 degrees Fahrenheit. He set the point at which still water just began to form ice on its surface as 32 degrees Fahrenheit. He set the temperature of the human body taken in the mouth or under the arm as 96 degrees Fahrenheit. All right, well, there we go. These may seem like odd numbers to choose, but consider that 64 degrees separate 32 degrees and 96 degrees, because 64 is 2 to the 6 Fahrenheit, could simply bisect or divide in half the distance between the two numbers 6 times in order to calibrate 1 degree. All right. Now, we've already covered that. Water boiled 180 degrees higher than it froze, and it readjusted the scales to make it exactly 180 degrees. Of course, we know that it's a different temperature Celsius, but that's the point. All right. And to convert, here's a little trick of the trade. To convert Celsius into degrees Fahrenheit, multiply the number by 1.8 and add 32. To convert from Fahrenheit to Celsius, subtract 32 and divide that number by 1.8. There we go. All right, now the second question is, why or how was the Rankine temperature scale developed? Okay, let's see. All right, the Rankine scale is a thermodynamic absolute temperature scale. It is based around absolute zero. Now think about that for a minute. That's pretty cold, guys. That is deathly cold. You and I couldn't survive that. Rankine is similar to the Kelvin scale in that it starts at absolute zero. And zero Rankine is the same as 0 Kelvin. Wow, how about that? But it is different as a change of 1 degree Rankine is the same as a change of 1 degree Fahrenheit and not 1 degree Celsius. Note that the abbreviation R is ambiguous as it can also refer to the Reaumur scale. Well, we're not talking about the Reaumur scale. The Kelvin and Rankine temperature scales are defined so that absolute zero is Kelvins, K, or 0 degrees Rankine. The Celsius and Fahrenheit scales are defined so that absolute zero is negative 273.15 degrees Celsius or negative 459.67 degrees Fahrenheit. So, even though it's this negative number Celsius or this negative number Fahrenheit, it's still going to be absolute zero, either in kelvins or Rankine. All right, the Rankine scale was originally used in the United States and France. Okay, well, let's see. Let's see how this came to be. All right, this article is about the temperature scale of Rankine. Okay, it's an absolute scale of thermodynamic temperature named after the University of Glasgow engineer and physicist Macquorn Rankine, who proposed it in 1859. Similar to the Kelvin scale, which was first proposed in 1848, zero on the Rankine scale is absolute zero, but a temperature difference of 1 Rankine degree, RA, is defined as equal to 1 Fahrenheit degree, rather than the Celsius degree used on the Kelvin scale. There you go. In converting from Kelvin to degrees, Rankine, 1 degree Rankine equals 9 9/5 Kelvin, or 1 degree Rankine equals 1.8 Kelvin. A temperature of 0 degrees Kelvin, or negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit, is equal to 0 degrees Rankine. Usage. The Rankine scale is still used in engineering systems where heat computations are done using degrees Fahrenheit. Yes, I know. I'm personally comfortable with the Fahrenheit scale, but our instructor uses the metric scales like the Kelvin scale and the Rankine scale and the Celsius scale, which we'll be using a lot. Okay, great, wonderful. I'm just kidding, Carlos. You know I am. I'm actually been very interested in this class. It's been a lot of fun. But anyway, moving right along. All right, now the symbol for degrees Rankine is R, or RA if necessary to distinguish it from the Romer and Reaumur scales. By analogy with the SI unit, the Kelvin, some authors term the unit Rankine, omitting the degree symbol. Some temperatures relating the Rankine scale to other temperature scales are shown in the table below. Okay, here we go. Absolute zero, 0 degrees Kelvin. Celsius, negative Fahrenheit, Rankine, 0. Freezing point of brine, zoop, Kelvin. This much Kelvin, this much Celsius, this much Fahrenheit, this much Rankine. Freezing point of water, this much Kelvin, this much Celsius, this much Fahrenheit, this much ranking. Boiling point of water, this much Kelvin, this much Celsius, this much Fahrenheit, and this much ranking. All right. Let's see. There was another one here. And I think, did I go over? Yes, I think I did. Let's see. Yeah, here we go. All right, one last thing. This is from chemistry.com. Why do we still need to know about the ranking temperature scale? Okay. All right. Ranking is commonly used in the aerospace industry in the United States. I know, that's true because our instructor used to work for one of the aerospace companies, which is pretty cool in itself. All right, except all cookies. Ranking is to Fahrenheit what Kelvin is for Celsius. So when people in the United States were creating programs and using equations that needed an absolute temperature, they used ranking before Celsius became dominant for scientific calculations. The reason people still sometimes use it in the aerospace industry is that there are a lot of programs that were developed using ranking. So in order to be compatible with the old programs, it's often simpler to just use ranking in the new programs too. There you go. Oh, this is from an intern at NASA. So I was writing simulations that used ranking back in 2009. There you go. Let's see. Yeah, most of us in the world use the Celsius scale to measure temperature from day-to-day purposes. The Kelvin scale has been designed in such a way that it is not only an absolute temperature scale, but also this makes conversion from Celsius to Kelvin pretty easily. Yeah. Okay. But yeah, so what do they do? Here's steps the ranking scale. The ranking scale is sort of like the Kelvin analog for Fahrenheit users. Ranking is an absolute temperature scale and has the property of having a 1 degree R change equal to a 1 degree F change. This means Fahrenheit users who need to work with absolute temperatures will find it easier to use the ranking scale instead of the Kelvin scale. Fahrenheit can be easily converted to ranking by using the following. R equals F plus 459.67. All right, there you go. Yeah, the ranking scale. The Rankine scale is an absolute scale of thermodynamic temperature named after the Glasgow University engineer and physicist William John McCorn Rankine, who proposed it in 1859. The Kelvin scale was first proposed in 1848. It may be used in engineering systems where heat computations are done using degrees Fahrenheit. All right, there we go. I hope that answers the questions. And like I said, I will have the links to these in the description box below. I hope this answers the questions that were given me. I think they have. I actually think some of them even answer both questions in number 1 and number 2. So, without further ado, I'm going to put a stop here. Oh, sorry. My apologies, Carlos. It's over 5 minutes, so my apologies. But I hope this answers the questions. Thank you for stopping by Shadow X&One's Garage. And I hope to see you guys in the next video coming up soon. All right.